You are listening to The Vocal Technologist. Spoken tech for your ears.
So the bit rattling around my head is this. We are throwing petabytes of data at every problem, but the smartest companies right now are actually figuring out how to do less.
Yeah, which is completely backwards to how the tech industry has operated for, well, a solid decade, right?
Right, it really is.
Because the old playbook was just brute force, hoard everything, keep every single log, run the absolute most massive foundation model you can get your hands on, buy more servers, and basically figure out the bill later.
Yeah, and that is exactly what we are going to untangle here on Vocal Technologist. We're going to take a proper look at how the biggest tech players, places like Netflix, Meta, DoorDash, are ripping out all that bloated infrastructure.
Absolutely.
We'll get into how they are reining in runaway AI costs and why relying on the average metric on your dashboard is completely dodgy.
It's a massive pivot. And you see it clearest in how companies are handling this current AI boom. Because they aren't just adding more hype to the pile. I mean, they're actively building fences.
Right, and if the goal is building fences around AI, you run into an immediate physical problem. Like, how do you actually stop a language model from endlessly pinging your internal databases until the servers physically melt?
Yeah, it's a huge issue.
Because DoorDash just built this massive centralized agent gateway to deal with exactly that, right?
Spot on. Think about the mechanics of letting an AI agent loose in a corporate environment. It's not just generating text. It needs to look up live order histories, check driver delivery times, maybe process a refund for a customer.
It actually has to do things.
Exactly. To do that, it has to talk to your internal tools. So DoorDash uses something called MCP, the Model Context Protocol.
Okay, MCP.
Right. It basically standardizes how an AI talks to internal APIs. They have over 200 of these MCP servers running right now, handling millions of calls every week.
But if you just let an AI ping your internal APIs whenever it feels like it, I mean, that's like giving a toddler a platinum credit card in a toy shop.
It really is.
They're just going to go wild, pull everything off the shelves, get stuck in some weird reasoning loop, and rack up a massive compute bill before you even notice.
Well, it's worse than that, actually.
Yeah.
If you don't control the gateway, you also have massive security risks.
Yeah.
What if the agent hallucinates a command and tries to drop a production database table?
Oh, wow. Yeah, that would be catastrophic.
TrueScale requires a strict prepaid card system and basically a bouncer at the door. That is exactly what DoorDash's agent gateway is. It's a control plane. Instead of agents running wild, every single request goes through this one choke point.
So it manages the traffic.
Yeah, it handles the identity of the agent. It manages authorization, checking if this specific agent is actually allowed to trigger a refund. It filters out sensitive customer data before it hits the model. And crucially, it enforces hard rate limits.
So the AI physically cannot span the system. You've governed the chaos. And I reckon this ties directly into the other massive shift we're seeing, which is crashing costs, right?
Oh, totally.
Everyone assumes the competitive edge is having the absolute smartest, most massive AI model on the market.
But that assumption is just outdated now. OpenAI, rolling out GPT 5.6 Luna, completely shifted the economics. It's a smaller, much faster model. And it has made analytics incredibly cheap.
Well, how cheap are we actually talking? Because, cheap in enterprise tech usually still means thousands of dollars.
We're talking highly accurate SQL analytics costing under half a cent per query.
Wait, under half a cent? That completely changes the math for a startup.
It shifts the advantage entirely. It's no longer about paying a massive premium for a giant omniscient model just to parse some internal data. The real advantage now is having strong business context, a highly responsive data platform, and rigorous evaluation pipelines.
So you want a small, dirt-cheap model paired with lightning-fast infrastructure.
Exactly.
That makes total sense in theory, but I do have to push back a bit here. If you're relying on a smaller, cheaper model to do heavy lifting, especially for automated labeling or analytics, LLMs hallucinate.
They do, yeah.
I have to imagine automating that much introduces a massive margin of error.
Well, that's exactly why you need an evaluation pipeline, which is what Flipkart did with their product analyzer. They didn't just plug in a cheap model and hope for the best.
Right.
They automated their product relevance labeling. Normally, you have human reviewers looking at a customer's search query and the product match to see if the search engine is actually serving up the right stuff.
That sounds incredibly tedious.
It is. So Flipkart trained an 8 billion parameter reward model to do this instead.
But how do you force an 8 billion parameter model to not just guess?
First, they ran supervised fine-tuning on millions of examples, forcing the model to explicitly generate reasoning traces. It has to show its work, basically.
Okay, that makes sense.
Then, they use this reward model to score both the correctness of the label and the quality of the explanation it generated.
And does it actually hold up against human reviewers? Like, really?
The automated report it produces matches the manual human reports within 1%, but it operates at a 30% lower cost.
Wow, 30% is heaps when you're dealing with Flipkart's transaction volume.
Oh, absolutely. And this is where the tooling is finally catching up. There is a new open source project getting traction called Smeevils.
Smeevils?
Yeah, it's a lightweight Python command line tool built specifically to stop you overpaying for AI.
Oh, I like the sound of that. How does it work?
You literally write a plain text YAML grader script. You define your tasks, you provide the expected output, and then you just run it locally. It gets a bunch of different models, from massive frontier models down to tiny local open source ones.
So a full shootout.
Exactly. The script fires your prompts at all of them, grades the responses, and spits out the absolute cheapest model that meets your specific quality bar. You don't need a sledgehammer if a scalpel will do the job perfectly.
That is brilliant. But, getting your AI governed and finding a cheaper model is, frankly, just the glamorous stuff.
Yeah, the shiny layer.
The real heavy lifting is happening down in the core data infrastructure, because companies are suddenly waking up to the fact that their old data pipelines are just way too complex.
The complexity has absolutely reached a breaking point. Let's look at Netflix, right? They have this internal system called the time series abstraction. Its job is to store and query multi-petabyte temporal data sets.
Right.
We're talking over 15 petabytes of compressed cold data.
Wow. That is a staggering amount of data to keep actively searchable.
Now, previously, to handle this pipeline, Netflix relied on Kafka and Flink. They used them to stream data out of their hot Cassandra database and write it into S3 for long-term cold storage.
Right, so Kafka handled the event streams, Flink processed it all, and eventually it landed in S3 buckets.
Exactly.
Which sounds exactly like the standard enterprise playbook, honestly. If you have a data streaming problem, you throw Kafka at it.
But it added massive operational cost, and maintaining that pipeline was a nightmare. So what did Netflix do? They binned the middleman entirely.
Wait, really?
Yeah, they completely ripped out Kafka and Flink for this specific workflow. Instead, they built a native Cassandra cold tier that just reads directly from those S3 backups.
Hang on, they ripped out Kafka.
They did.
I have seen engineering teams treat Kafka like a religion. I mean, the operational pain of just managing zookeepers or even the newer craft protocols and balancing those partitions when a node goes down is notorious.
Oh, it's a headache.
You're saying they just removed it and the system got better?
Not only better, it got significantly faster. By cutting out the streaming middleman and reading directly from S3 natively through Cassandra, they actually improved their P90 latency, meaning the response time, for 90% of their queries by about 30%.
That is wild.
And they kept the exact same query API for their engineers, so nobody had to learn a new system. But under the hood, they stripped the engine down to its absolute bare metal.
You take away the moving parts, and suddenly you get 30% faster reads on 15 petabytes of data. But why was Kafka struggling so badly there in the first place, though? Well, this gets into what data engineers are quietly calling Kafka's broken promise. Kafka's partition stream model is fantastic for certain things, like a few massive fire hoses of data, but it is a really poor fit for what we call router-style workloads.
What exactly is a router-style workload?
Imagine you have millions of independently keyed, ordered logs, millions of tiny, separate, distinct streams of events.
Okay, got it.
Kafka organizes data into partitions, but if you have millions of unique keys, the overhead of managing all those tiny partitions across a cluster just chokes the system. It's too heavy. The metadata alone brings the cluster to its knees.
So you might not be dealing with 15 petabytes of cold storage like Netflix, but if you're currently writing a Kafka pipeline for a startup that could just be using standard object storage, you're actively burning your own runway.
Precisely.
So what's the alternative for these router workloads then? Just raw object storage. Object storage is the foundation. Yeah. But there's a fascinating new project called Open Data Log. It's built in Rust, sitting directly on top of object storage, and it uses a backend called SlatedDB. It relies on segmented storage and metadata-only splits.
Meaning what, in practical terms?
And it allows you to handle high cardinality log routing, those millions of unique keys we just talked about, orders of magnitude cheaper, because it doesn't carry the heavy partition baggage and cluster management of Kafka.
It just writes segments efficiently to cheap object storage like S3.
Yeah, that's it.
It's this massive cultural shift towards simplicity, which is exactly what we're seeing with things like Polars, too.
Oh, Polars is brilliant.
Yeah.
Contrast these massive distributed systems with what Polars allows a single data developer to do today.
Right.
With Polars, a team can prototype a complex ETL pipeline locally, right on their laptop, using a representative sample of data, say 10 megabytes.
Which is standard, right? You build it small on your machine first.
But historically, when you go to push that to production, you have to rewrite all that logic for Spark or some massive distributed cloud framework.
Yeah, completely different code base.
Exactly. With Polars, you use something called lazy frame queries. A lazy frame doesn't execute your code immediately. It builds an optimized execution plan.
Okay.
So you can use the exact same queries you wrote on your laptop, point them at a cloud bucket, and scale them up to run across 16 billion rows of Parquet data without rewriting a single line of logic.
The exact same code scales from a laptop to 16 billion rows. That is incredible.
Not a single line changes, and it's incredibly efficient. A pipeline can pre-aggregate raw, massive financial market data into small artifacts in S3. Then a front-end dashboard can just read those tiny artifacts and stay incredibly snappy.
Because it doesn't have to scan 16 billion rows every single time an analyst refreshes the page.
Spot on.
But here's the thing. If you are keen on untangling this kind of stuff with us, hit subscribe. Because all this lean infrastructure, all this brutal optimization, it is completely useless if your dashboard is lying to you about how well it's working.
It really is.
Let's talk about the math, because the way we measure performance in this industry is fundamentally broken.
It comes down to our obsession with relying on averages. There's a brilliant case study of an engineering team rolling out a change to their web service latency. They pushed the update, looked at their dashboard, and saw the average latency had risen by 9%.
9% slower. A bit ordinary. Maybe you'd want to suss out why it bumped up, but it certainly doesn't sound like a crisis that requires rolling back the deployment.
Right, looks completely fine. But then they looked deeper into the exact same data set. The median latency, the exact middle user experience, the 50th percentile, had actually fallen by 46%.
Wait.
Yeah, half their users were suddenly having a massively faster experience.
Okay, so the average went up, but the median went way down, which mathematically means...
Which means the worst experiences got catastrophically worse. When they looked at the P99 latency, the slowest 1% of requests on the platform, it had spiked by 119%.
So basically, the average user doesn't actually exist. We're designing infrastructure for a ghost.
That is a great way to put it.
You have a bunch of people having an amazing, snappy experience, and a handful of people timing out completely, staring at a frozen screen. And when you mash them all together, the dashboard just smiles and says, hey, 9% slower, nothing to worry about.
That is exactly the danger. A single metric like the mean hides a bimodal distribution. You literally have two completely different realities happening inside your system at the exact same time, and the average obscures both of them.
Right.
You have to look at density plots or shift functions. In this specific case, the root cause wasn't even the code being slow. It was the sheer size of the response payloads for that top 1% of users choking the network.
And this habit of designing for the happy path, designing for that ghost of an average user, it bleeds into everything, especially when it comes to databases.
Production databases absolutely fail at the edges. Everyone writes their tests for the happy path. A user clicks buy, the inventory decrements by 1, the receipt generates, the email sends. Beautiful.
But the real world is incredibly messy. Networks drop, people double-click buttons.
You get stale replica reads, where a user queries a secondary database node just milliseconds before the primary node is finished syncing the new data. You get deadlocks, where two transactions are competing for the same row and waiting on each other forever.
Stuff that just quietly breaks everything.
Exactly. You get live migrations that just quietly break transaction flows. These are the silent failures that don't show up on a basic dashboard.
So how do you actually fix it? I mean, you can't just write more happy path tests and hope for the best.
No, you have to enforce invariance at the boundary.
Break down how that actually works in practice.
It means you do not trust the application code to behave nicely. You enforce the absolute rules inside the database itself. You use guarded writes. You strictly limit transaction times so nothing hangs indefinitely. You build in idempotent retries.
Idempotency is essentially an already done stamp, right?
Exactly. If a mobile network blips and the server gets the same charge this customer $10 request twice, The database sees the idempotency stamp and just ignores the duplicate.
Ah, so it doesn't charge them $20.
Right. You have to treat the production database as a hostile environment where edge cases are the norm.
Because if you just trust the managed cloud service to magically handle the complexity for you, you end up on the front page of the news. Imagine the sheer panic of being an infrastructure engineer and realizing Microsoft just handed out your master keys.
Yeah, the Azure Cosmos DB incident was a sharp reminder of exactly that. Microsoft almost exposed the master read-write keys to thousands of customers' Cosmos DB instances.
Just a total nightmare.
It proves that relying purely on managed cloud platforms to handle your infrastructure without your team doing regular, rigorous cloud secret rotation reviews is a massive risk.
And when things do go wrong, whether it's a leaked key or just a bad script, you need to know who did it. Which brings us to audit logs. Everyone records database audit logs for compliance, but nobody actually reads them.
Nobody reads them because they are largely useless in their raw binary form. If you look at a raw MySQL audit log, it might just say a specific row was modified or deleted. It doesn't tell you the context. It doesn't tell you the intent.
So it's just a graveyard of useless data.
That's why tools like dbTrail are becoming critical for lean teams. dbTrail actually parses those logs and links the row changes to the specific session identity, the actual SQL statements executed, and crucially, what the data looked like before the change.
So instead of just seeing row 5 deleted, you see the junior dev's migration script deleted row 5 at 2 a.m. and here's the exact undo script to put it back.
Yes, it makes the logs actionable. It generates transaction scope reversal SQL so you can actually restore the affected data in seconds rather than spending hours trying to piece together a backup.
Man, all of this, the hidden latency spikes, the unread binary logs, ripping out Kafka, it really ties into how the biggest company on Earth handles scale.
Let's look at Meta.
The engineering lessons coming out of Meta's data platform are a masterclass in sweating the small stuff. Sridhar Iyer recently shared some deep technical details about how their internal data platform evolved.
Right.
One of the most fascinating takeaways was their realization about data hoarding. They realized they were keeping absolutely everything, just in case. So they decided to truncate a single debug column in one of their logs.
Wait, just one column? You have got to be having a lend.
Just one single column, and doing that saved the company millions of dollars.
Millions from a string column. How massive is that table?
You have to remember, Meta operates at a scale most people simply cannot conceptualize. We are talking trillions of events.
Oh, wow. When you have petabytes of data flowing through a pipeline every single hour, a single bloated debug string column, replicated across dozens of massive data centers for redundancy, adds up to massive storage and compute costs. By truncating it, the savings on disk I/O and storage are instantaneous and permanent.
That is staggering. But I imagine there's a flip side. You can't just go around deleting everything to save a buck.
No, and they learned where they absolutely cannot delete data too. For their core tables, the foundational data that serves up to 50% of their entire massive data warehouse queries, they realized they can never just delete or overwrite old data.
Right, because the blast radius is too big.
Exactly. It requires strict immutable versioning. If you break a core table with a bad update, you literally break half the company's analytics overnight.
So they are absolutely ruthless about deleting the noise, but incredibly protective of the core signal.
Yeah, and that same philosophy of aggressive, detail-oriented optimization applies to their AI training as well. Meta recently scaled their ads recommendation foundation model, making it 4 times larger in just 12 months.
4 times larger? Usually when a model gets that much bigger, your compute costs go through the roof and your actual hardware efficiency just drops off a cliff.
Normally, yes. But Meta actually doubled their training efficiency to reach 20 to 25% MFU.
MFU being model flops utilization.
Right. It's a metric of how much time the incredibly expensive GPUs are actually doing math versus just waiting around for data to arrive over the network.
Ah, gotcha.
Hitting 25% is exceptionally high for a distributed model of that scale.
How did they manage to double the hardware efficiency while the model got 4 times bigger?
By sweating the deepest technical details of the training pipeline. For instance, they implemented something called jagged flash attention.
Okay, you're going to have to explain the mechanics of that.
Well, when you train a model, you feed it sequences of data sentences, basically. But the sentences aren't all the exact same length. Normally, you have to pad the shorter sequences with empty data, zeros essentially, just to make the math matrix work efficiently on the GPU. That padding is wasted compute cycles. Jagged flash attention dynamically handles the varying sequence lengths, eliminating that padding waste entirely.
So the GPU is only ever crunching actual valuable data, never filler.
Exactly. They also implemented an SM-free collective communication setup.
Another one we need to translate.
Right, so in a massive GPU cluster, the chips have to talk to each other constantly to share weight updates. Usually, managing that communication over the network eats up compute resources on the chip itself, specifically the streaming multiprocessors, or SMs.
Okay, I'm following.
Meta figured out a way to offload and handle that communication without tying up those specific processors, reclaiming hardware capacity purely for training the model.
It makes you wonder. If the smartest move right now is ripping out massive infrastructure, truncating data we've hoarded for years, and shrinking our models to be hyper-efficient, at what point does doing less turn into realizing we never actually needed half the bloated tech stack we built over the last decade in the first place? Vocal technologists, see you soon.
Spoken Tech for your ears.